Carlo Rovelli, 7 Brief Lessons on Physics. Embark on an enlightening journey through the fascinating world of physics with Carlo Rovelli's 7 Brief Lessons on Physics. The book's summary takes you through pivotal theories, discoveries, and developments in physics over the years, from Einstein's theories of relativity to the seemingly incomprehensible realm of quantum mechanics. Explore how our understanding of the universe has evolved, how we've begun to peer into the world of elementary particles, and how modern physics grapples with an ongoing quest to resolve the paradoxes between general relativity and quantum mechanics, in search of a unified theory. This summary will help you comprehend the vast implications of these theories and their impact on not just the physical world, but also on our very existence.
Einstein's theories of relativity. In 1905, Einstein introduced his theory of special relativity, which states that time is relative depending on the conditions surrounding a person. This theory gained him instant notoriety, but it was in direct conflict with Newton's theory of gravity. Einstein spent 10 years working on his theory of general relativity, which proposed that the gravitational field is the space and not just something that fills it. This theory explains how space curves around massive objects and exerts a gravitational force that keeps things from flying away. Einstein's work provided a perfect launching pad for further theories. The emergence of quantum mechanics. Quantum mechanics is the scientific field that helps us understand the behavior of subatomic particles. It all started when German physicist Max Planck introduced the concept of energy packets. Later, Einstein confirmed it by discovering that light is made up of energy packets called photons. Quantum leaps, discovered by Niels Bohr, allowed electrons to jump from one orbit to another around the atom's nucleus. Werner Heisenberg then suggested that observing an electron was necessary for it to exist, and if not, its position could only be predicted probabilistically. The equations generated by quantum mechanics are essential for scientists in various fields like biology, chemistry, physics, and engineering. The evolution of our understanding of the universe. In the book Snippet, the author traces the evolution of human understanding of the universe, starting from the flat Earth concept to the present day. Prior to ancient Greek philosophers, the world was believed to be flat with the sky above it. The Greeks recognized that the sky is around us and made further observations suggesting that the Earth is a sphere. However, they also thought that planets and stars rotated around the Earth until Copernicus suggested otherwise. Telescopes gave us better knowledge of the cosmos, and physicists discovered that our galaxy was just a speck in a vast universe of galaxies. Einstein's theory transformed the conception of space, describing it as curved and identifying black holes as gaps in this curvature. Finally, the expanding universe theory explained that the universe began as a small, hot, and dense spot that eventually exploded. The particle universe. The microcosmic universe of atoms and particles is a complex and mysterious world that forms the building blocks of our physical and visual reality. The elementary particles that make up atoms, including protons, neutrons, and quarks, behave in unpredictable and non-geometrical ways, in contrast to the straightforward mechanical behavior of larger things. Even a seemingly static object, such as a rock, is merely a temporary arrangement of molecules and ultimately an event. The standard model of particle physics has been successful in experiments, but it is a collection of formulas rather than an elegant theory like those of Einstein. Our understanding of the particle universe remains incomplete, and we may be waiting for a new theory to bring together these loosely assembled formulas. The search for a unified theory of nature. General relativity and quantum mechanics are in conflict, creating a paradox that physicists are working to resolve. Enter loop quantum gravity, LQG, a top contender for a unified theory of nature. LQG's theory that space is made up of imperceptible grains called loops, not found within space but are space, partly resolves the paradox. LQG also suggests that time has its own varying rhythm for each process in nature and that the Big Bang may have been a big bounce. The science of heat. The field of thermodynamics that explores the science of heat was born out of one question: what is heat? The answer lies in the atoms of an object moving rapidly, generating friction and creating heat. While the concept of why an object gets hot is easily understood, the transfer of heat between two objects is due to chance. The 19th-century physicist Ludwig Boltzmann theorized that objects hot and cold meet purely based on statistical probability without a law of physics that states heat must be transferred. Heat also affects our perception of time, as seen in a freely swinging pendulum that loses energy due to friction and heat. Without heat, the pendulum would continue to swing forever, and the notion of time as we know it would be lost. The fascinating connection between humans and the universe. Human beings are inherently curious, just as the physicists who study the world around us. Despite our capacity for discovery, we often forget that we, too, are part of the same universe that we study. The same laws of nature that govern the stars in distant galaxies also shape our very existence, including our thoughts, feelings, and consciousness. While we may feel as though we have free will, our actions are ultimately determined by the laws of nature, just like any other event in the universe. Moreover, everything in the universe has a natural fate, and our species, too, will eventually perish. Despite this, we remain dedicated to uncovering the secrets of the universe, even if that means confronting our own impermanence.
As we conclude our eye-opening journey through the summary of 7 brief lessons on physics, we are left with a newfound understanding and appreciation for the countless breakthroughs and ever-evolving world of physics. From Einstein's groundbreaking theories of relativity to the mysteries of quantum mechanics, our comprehension of the universe has come a long way, with each discovery unlocking new avenues to explore. Furthermore, we also come to realize that our actions and existence are intertwined with the laws of nature. While the quest for a unified theory continues, one thing is certain: the human spirit for exploration and discovery remains unquenchable, driving us to uncover the wonders that our vast universe has to offer.